Okay, so let's continue with electricity and magnetism and get into the electric fields topic proper, and look at Coulomb's law. Okay, let's get into the nuts and bolts of what we need to know for Year 12 physics about electric fields after we've done that brief introduction. And really what we need to be able to do initially is to work out the amount of force between two charged objects. So we just looked at some examples of charged objects interacting. We also, I guess, talked about the direction, and I'll just highlight that stuff again. But we also need to work out the size of that force. And we do that using something called Coulomb's law, which is what I have written here and is the title for our topic. So the three intended student learnings for this slide, and I'm really going to focus mainly on the first one, is solve problems using Coulomb's law. It just defines what they are. You then need to, in a similar way to we did in the last topic, use proportionality to solve problems. Remember that there is the Essential Skills video on proportionality. I'm not going to talk a lot about that today. You can go back and review that because all those same concepts apply. And obviously we need to understand that Coulomb's law, like all our laws to do with force, is consistent with Newton's third law. And that's pretty straightforward. So, firstly, we might start in the middle. Often when we talk about forces, we talk about both the direction and the magnitude. The direction stuff is fairly easy. With gravity, it was always attractive, so it was always towards each other. With electrostatics and charge, we can have two different possibilities. Where we have unlike charges or opposite charges, they will attract each other. However, where we have like charges, i.e. two positives or two negatives, they will repel each other. Oops. Now, these charges, the force that each charge experiences is what we call mutual. So the force that the positive attracts the negative is equal to the force that the negative attracts the positive. Therefore, they're equal and opposite. The action force, there's an equal and opposite reaction force, so it's obviously consistent with Newton's third law. Same with the repulsion. The force that this charge repels this charge with is equal to the force that this charge repels this charge with, so it's consistent with Newton's third law. Now, to work out the magnitude of the force, so the size of the force, we use Coulomb's law, which basically says that force is equal to 1 on 4 pi epsilon naught, and that's just a constant. All that together is equal to, it's on your formula sheet, 9 times 10 to the 9. And then we use the two charges, the product of the charges divided by the distance, which we define as r squared between them. So, in words, the magnitude of the force is directly proportional to the product of the two charges, and inversely proportional to the square of the distance between them. Inversely, on the bottom, proportional to the square of the distance between them. You can probably see this looks a lot like our law for gravitational attraction, but in that case the constant was g, not 1 on 4 pi epsilon naught. We talked about the product of the masses, and inversely proportional to the square of the distance between them. The thing I would like you to note though is that the electrostatic force is much stronger than the gravitational force. And to get an indication of that, we can look at the constant of proportionality. So that is g here, that's 1 on 4 pi epsilon naught there. Here it has a value of 9 times 10 to the 9, so 9 billion. Here the constant has a value of 6.67 times 10 to the minus 11. So, for those familiar with indices, that's like 20 orders of magnitude. 10 times 10 times 10 times 10, I could go on 20 times stronger. So we get a much stronger constant of proportionality. Yeah, typically when we deal with masses, if we think about everyday masses, they might be of the order of kilograms. Everyday charges might be of the order of microcoulombs, which is a millionth of a coulomb. But a millionth is 10 to the minus 6. So 10 to the minus 6 does not counteract that difference of 10 to the 20. So typically electrostatic forces are much stronger for similar objects than the gravitational forces. Okay, that's it. Thanks. Okay, now we're going to combine Coulomb's law with some vector addition. Now we call the fancy name for this is the principle of superposition. But basically what that means you need to be able to do is, using vector addition, calculate the magnitude and direction of the force on a point charge due to two other point charges. Got an old exam question here to show it. So we've got a charge QA, a charge QB. We're going to work out the total force on this charge here, Q, due to these two forces. How do we do that? Well, when more than 2 point charges are present, the force on any one of them is equal to the vector sum of the forces due to each of the other point charges. So, work out the force, pardon me, work out the force here on Q due to QA, work out the force due to QB, add them together vectorially to work out the net force. Now this question might seem a bit tricky, but it's actually trying to help us out because it's told us charge Q experiences a force towards the east of magnitude 2.9 times 10 to the 24 newtons due to QA. So we know that due to QA, we get a force in that direction. That's the force due to QA. And we know that's 2.9 times 10 to the 24 newtons. We then, and this is what it asks us to do in part B, can calculate using Coulomb's law the forces it experiences due to QB. This is a positive, this is a positive. I've sort of crossed it out, so that force will be downwards. But when we do a vector addition, that'll come here. So this will be the force due to QB. Then, to work out the total force, we're going to add them together vectorially. So I haven't worked out the numbers yet, but I'm just showing you the concept of how we do that with vector addition. So now let's fairly quickly go through and show how we do that with numbers using Coulomb's law that we had on the previous slide. So part A, calculate the magnitude of the force that charge Q experiences due to QB. We use our Coulomb's law, we're working out the force due to QB. So we're between QB and Q, we plug all those numbers from the question in, and we get 2.88 times 10 to the minus 24 newtons, which if we went to two significant figures, which we probably should because we only get two significant figures for some of our charges and distance, is actually the same magnitude of the force that we had due to QA. So as often, when they set these tests and exam questions, they're not trying to make them too difficult, they're trying to make them easy for you. So, there we have it. We've worked out part A, the force, using Coulomb's law, we've worked out the force that Q experiences due to QB. So part B, calculate the magnitude and direction of the total force acting on Q. So now we're going to do this vector addition of these two forces, and we use our old Pythagoras because we've got a right angle triangle. One of the forces is, if you like, south, one's east, they're at 90 degrees to each other. So we plug this into our Pythagoras formula, and we get 4.1 times 10 to the, and that should be minus 24. Always check for the reasonableness of your answer, newtons. So that's calculated the magnitude. Now we need to calculate the direction. And to do that, we're going to need to use some trig. Okay, so we actually know all three sides of this triangle now, so we could have used sine, cosine, or tan. I've just chosen to use tan because I think it works out simpler. So tan theta equals opposite over adjacent for this angle here. Those two numbers we just worked out before are basically the same if we go to two significant figures. So anything divided by itself equals 1, and you may even remember that the tan of 45 degrees equals 1, so we work out that theta equals 45 degrees. And if we want to define that direction a bit more clearly, that is east 45 degrees towards the south. We could have gone south, 45 degrees east. Or if we're a good orienteer or sailor or something like that, you could have probably just said southeast, because southeast assumes it is directly between south and east. So there we have it. We've worked out both the magnitude of that force, and we've also worked out the direction of that force.